Welcome to this e-lecture, which will be about a well-performing regression model, the so-called R-square. This is about regression analysis and how well-performing our regression model is. So when we do regression analysis, we want to do predictions. We want to predict values on the dependent variable y, for example, by setting a value for the independent variable x into the regression equation. And for example, what is the average life expectancy in a country where the government's share of health expenditures is 40%? So then we can use the regression equation, and we have the constant and the regression coefficient, and then we put in 40%, and then based on the regression equation we expect or predict that life expectancy in a country where the expenditures is 40% will be 66.4 years. But when we do these kind of predictions, we have to be aware that we have an error term, things we do not explain, or also called the residuals. And it's important to know that single observations can deviate a lot from the regression line, which is our prediction. And the deviation between the actual value, which is y without a hat, and the predicted value, which is y with a hat, can be quite large. These are the residuals, which is the difference between the observed y value and the regression line. And that says by how much we miss when we predict the observation by means of the regression line. So when we want to predict this unit's value on the dependent variable is actually somewhere below 50, but when we use the regression line, we predict it to be somewhere above 70 years. So it's really we miss quite a lot when using the regression line for prediction. But why do we use the regression line for prediction, and when we miss quite a lot? Well, it's way better to use the regression line for making predictions than for using what is next best, which is the average. And so let's compare the average and the regression equation when it comes to predictions. Really, the R-square says how much we can reduce prediction error by using the regression equation instead of the average. That's what R-square tells us, or that's one interpretation of R-square. So if we have the average, what information do we use? Well, we have only information about the dependent variable if we are making predictions based on the average. And our best guess of a unit's value on the dependent variable is the average of that dependent variable. But when we use the regression equation, we have information about the dependent variable and information about the independent variable, and we can predict value. The predicted value can be based on the regression equation. And let's illustrate this prediction based on the average and the regression equation. Well, if this line here is the average on the dependent variable y. And the distance from the actual value on y for this unit to the average can be called the total sum of squares. But when we use a regression equation, which is this line, we explain this much more of the total sum of squares, whereas for this unit there is still this unexplained sum of squares, but we explain much more of the total sum of squares, or the variation, so to speak. So we reduce for this unit we reduce the miscalculation by this amount. So we kind of hit that is not that's we of course we still doesn't really predict a totally correct value, but we are much closer than just using the average. So how is this calculated? Well, the calculation of R square is you take the sum of the square deviations from the mean, and then the sum of the square deviations from the regression line, and then you look at the reduction in the deviations using the regression line instead of the average. And then R square is how much less the total square deviations from the is the total square deviations from the regression line versus the total square deviations from the mean. How much less those total square deviations are. So it's really two possible interpretations of the R square is really how much of the total variance or variation in y, the dependent variable, that it's explained by the regression model, and how much prediction error for y is reduced by using the regression line instead of using the average on y. So back to our example with life expectancy as the dependent variable and government share of health expenditures as the independent variable. Well, if we use the regression model instead of the average on the dependent variable, the prediction errors decrease by 18%. As you can see here, the R square is 18%, so we reduce prediction errors by 18%, which is, yeah, I mean, that's quite good. Often we will interpret the adjusted R square because R square, this line will be even better fitted when we add more independent variables, when we go from the bivariate to the multivariate regression model. So then often the R square will go up, and we want to adjust for that, and then we use a little bit more conservative measure, which is the adjusted R square, and so this will often be a bit lower, have a bit lower value than R square, but both are good. We can use both, but by using but the main point is that by using the regression model instead of the average, we decrease prediction errors by in this model 18%. So that was the e-lecture on a well-performing regression model and the interpretation of R square. Thank you so much.